Hello everyone. So yeah, JavaScript from scratch. So what I mean by that is, what if all you have are functions, right? You have no numbers, you have no booleans, you don't have if, none of these things. How do you get them back if all you have are functions? Now I've got a preface. I spent a long time trying to figure out how to give a practical reason for anyone wanting to know this. Like several days were spent on this. There is no good practical reason, okay? So this talk goes to impractical extremes in almost every way. So I'm live coding the entire thing, and even the contents page looks like this. There's a reason for it, but again, it's an impractical one. So and the reason why is there's so many things that you can cover in this space. So I kind of wanted to give everyone here a choice. This is going to be an interactive talk. I have a bunch of topics here, and after every one we've done, you can kind of pick a new one. So for instance, we can only start with this thing called combinators, which is the first one here. But after that, you can do anything that points to combinators. So you can do, for instance, booleans, or a little bit further down, you can do this thing called natural numbers. And once you've done booleans, you can do if expressions, and, or, not, that kind of thing. Right? Does that make sense? Yeah, good. And so also, I mean, I know quite a lot of you kind of want maybe a motivation, even if it's not a practical one. So here's a picture on a page for you. Okay, you're stuck on a desert island, and all you have are functions, and you have to rebuild society and live in a normal way. That's the best I could come up with after a few days. So without further ado, shall we start with combinators? That's the only place we can start, right? So combinators. It's just a fancy way of saying a function that takes functions as arguments, returns a function, and whilst it's doing that, it only uses functions. So it's kind of just reiterating what I said before. We have a functions. And to define our combinators, we're going to use JavaScript's arrow function syntax. So if people aren't aware of it, it's fairly simple. So what we do is the parameters, they go in brackets. So this ID has one parameter, it's x. And then you have an arrow, and then after that arrow goes the body. And if you don't have anything except a return and an expression, you can get rid of the braces and you can get rid of the return. So this thing here that I've just written is the same as writing all of this. So you can see why I've chosen the arrow function syntax. We're going to be writing a lot of functions, so we want to make it as easy as possible for ourselves. This next, so I should probably say ID, stands for identity. And the way you can remember that is you give it a thing and it just returns the identity of it, just gives it back unchanged. So constant stands for the constant combinator, and what it does is it takes parameter x and it returns another combinator which takes parameter y, ignores it, and constantly gives you back x. So that's why it's called constant combinator. And finally comp, that is its function composition. So it takes two combinators and it returns a combinator, and that combinator applies g and then f to x, and it's that way around, g then f. And especially const and ID, they might seem a bit useless right now, a bit esoteric, but actually we'll find lots of uses for them. And because we're good software engineers, even on the desert islands, we have assertions. We have an assertion function, and it just prints out nice little ticks, Unicode ticks for us. We also have Unicode on the desert island. And yeah, so if an assertion turns out to be wrong, then we get a little cross, and we can fix it, and then be happy. So that's how we're going to do most of our coding here. You can just imagine, if you want further metaphor into desert island, the assertions are in our mind. They're what we remember of the mainland. And we also have this function called Stringify, which does a slightly strange thing. So probably the easiest way of showing what it does is just using this f and g that I defined using Stringify. What it essentially does is it prints out the function call that it would have made, right? So you can see at the bottom here, it prints out f1, g1, and fg1, and that just came from the log of that. And all this code is online, so you can see what terrible hackery I did to get that. But what we will use that for is, because we're using functions and we can't really look inside them normally to test for equality, what we can do is we can feed these kind of functions in and see how they're used. And that will turn out to be super useful when we're dealing with things like numbers and lists, which kind of use functions in funky ways. Okay, so that's all we have at combinators. We're going to shoot back up to the contents page. And now we have to pick a new thing. So I want audience participation for this. So the choices are, and it goes roughly in this order for difficulty, right? Booleans, natural numbers, pairs, optionals, and lists. Okay. So who's for natural numbers? Hands up. Who's for booleans? Sorry, I've gone in the wrong order here. So and then pairs. Oh. Okay, good on you. Optionals and this. Okay, good. So booleans, right? Sensible people, generally. Okay, so booleans are perhaps the simplest you can get for data structures. We have some tests here. Now the way we're going to be testing what I'm going to call these encodings, ways of getting booleans out of functions, is using these kind of translations. And again, using the desert island metaphor, what I'm basically saying is, say, upon your subsequent rescue, and you're talking to a JavaScript developer, and seeing as you've been cast away for so long, you've actually forgotten what booleans are on the mainland. All you know are these functions that you wrote, and they seem to do a pretty good job for you. But you want to kind of make sure. So what you do is you find a way of translating mainland booleans to desert island booleans. And what I'm going to say that is this from bool function, and a way to translate your desert island booleans to mainland booleans called toBool. And if you can do that back and forth and get the same thing, you're in business, right? Because then you can kind of have a conversation with your mainland JavaScript developer. And now the tests only go one way. They only test that if you translate from a mainland boolean to a desert island and back, you get a good thing. You should test the other way, but it's difficult to do because you have functions, and testing equality of functions is really difficult. So you'll have to take my word for it, or resort to mathematical proof. That's your choice. And I've been kind. I've given you the from bool translation here. It's very simple. So I've been naughty, and I've assumed that bool is actually true or false, right? Which obviously in JavaScript is probably not true. They could have given you anything. But we'll assume bool is true or false, and I say if it's true, or if it's truthy, return this thing called t, and if it's false, return f. And so we have to define t and f using just functions. So let's kind of get to grips with what it actually means to be a boolean in this desert island world. So first and foremost, it has to be a combinator, right? Because that's all we have, be a function. Secondly, t and f have to have the same interface. Because you expect to use them in roughly the same way. What it means to have the same interface for a combinator is, roughly speaking, it takes the same number of arguments, right? And then finally, the only thing that makes it a boolean is t and f are different from each other, right? Because if they were the same, that would be a terrible world to live in, right? Okay, so that's kind of what we have to begin with. We can start from the very bottom, right? What if we had no parameters, right? It's a combinator that has no parameters, and t has a body, t's body, and f has f's body. Okay, well, they are combinators, and they do have the same interface. Now, to make them different from each other, tb and fb have to be combinators, have the same interface, and be different from each other. So this is a bad place to start, right? We need more than no parameters, right? And actually, we kind of run into the same problem if we just have one parameter. Because, okay, then tb and fb can be different if they do something different to their parameters from each other. But actually that just means, applying a different function. So again, we kind of move the problem slightly away, but still, we have to solve the whole problem for tb and fb, these things here. Actually, what you should do is have two parameters, right? If you have two parameters, then does anyone have like an inkling as to how you'd make T different from F? Yeah, just shout it out.
Well, you return T and F from the first one and F and T in the second one. Reverse order.
Okay, so we can. That's okay. So we reverse order, yeah. But then we only have functions. This is the thing. So we can have no way of packaging together T and F. That's a very good idea, yeah.
Which order you call the functions in?
Yeah. So there's this idea of order. We can go one simpler than that actually.
It always produce the opposite output.
Yeah, essentially. So what we're going to do is T is going to return T, and F is going to return F. So I'll try to use some subtle psychological bias there, naming parameters. So this is an encoding for true and false. We don't actually know if it's a good encoding yet because we haven't translated back. So we'll have a look at that. We have to define this. Let me get the definitions back up. We have to define this tuple. Tuple takes this desert island boolean, which I call bool f or bool function, and it has to give us back true if we gave it the big capital T, and false if we gave it capital F. Right? Now, one way you can think of this is you're consuming like this combinator to produce a mainline boolean. And how do you consume a combinator? Well, this is going to come up all the time. You consume a combinator by applying it to something, right? So we have to apply it to something. The question is what? So we have to figure out what this T and F is, right? The T and F. So we can figure that out by looking at what would capital T do if we fed it T and F, little t on the left. Sorry?
Return T.
It'll return T. And what do we want it to return?
T.
Well, we want it to return true, yeah. So we will make T true. And similarly, we'll make F false. And in this way, we should get our encodings. Yay! So we have booleans, okay? What next? So there's two branches you can go down now. We can go further down the rabbit hole with booleans and do if expressions and or not, or we can do natural numbers. So who wants to go further down the rabbit hole? Okay, and who wants to do natural numbers? Okay, further down the rabbit hole. If expressions. If expressions are actually kind of deceptively simple with this kind of encoding. We'll do the same thing we did before and figure out specification. So if is a combinator, and we're going to say it takes three things. The boolean to condition on, which we'll call C, the thing to do in the then branch, and the thing to do in the else branch. And when it's true, we want to do one thing, and when it's false, we want it to do something else. So if it's true, we want it to give you T. If it's false, we want it to give you E, the else case, right? Yeah. But there's a bit of a problem, because if is a function in JavaScript, which means that before if even gets a hold of T and E, we're going to have evaluated all of it already. So what if T and E are really both expensive computations? And we actually only want to run the one that we should run if the condition is true or false. Yeah? What do we want to do then? Well, we kind of want to halt the computation of both of them and have if decide and then run the one that we want. So the way we're going to do this is we're going to say in our kind of interface, T and E are going to be combinators that only take one parameter. And then if is going to run them. So this is actually the specification of if. Right? So if you give it a true, then it'll take T and run it. If you give it a false, it'll take E and run it. So how do we do this? Well, we know how it starts. We know it's a three-parameter combinator. And so I'll tell you in English, and then you can see if you can drive me for a bit on the keyboard. So what we're going to do is we're going to use C to pick between T and E, and then we're going to call it. So C is, booleans in this case are kind of like pickers. They pick between the two things you give them. And in this case, we want to pick between these combinators T and E, and then run the one that we pick. Right? So what's the first thing that I've got to do here? C, brackets, yeah. T and E, yeah. And then another bracket, yeah. That's exactly it. And this is if, using this Boolean code. I actually have no test for if, because I'm being a bit naughty. But there's lots of tests to come for and or and not. So who wants to go further down the rabbit hole still, to and or not? Or go to natural numbers? All right, rabbit hole. Okay, so and we do have tests for, because we know exactly what all the cases are for and. Yeah, lots of errors and pain. So we know some things about and. We know that it takes 2 booleans, so that's a good start, left and right. And we'll be optimistic. We'll just return true. And well, most of it is false, because that was a bad choice, because and is false most of the time. Okay. Right. 3 out of 4 tests have passed, so this is a pretty good go. But no, so what we should use is if. We should use if to figure out what to do with our now, right? So we're going to do some classic short-circuiting in this case. So we're going to condition on the left-hand side. So we're going to assume they're both booleans, and then we have to choose 2 cases. So this bit will happen if L is true. If L is true, then what should we do? Well, this is and. So yeah, we can do if R, right? We need to condition on R. But actually, that's a lot of work, because what we're going to do is if R is true, we'll return true, and if R is false, we're going to return false. We're going to assume that they've given us booleans, we'll just return R in this case. But if L is false, then the result of the whole and is false, right? So this is the entire definition of and. Right? All tests passing, right? And similarly, or kind of works in the same way. I'm actually going to comment out these tests here for and, because screen real estate problems. So, and again, it takes 2 parameters. It conditions on the first one. But here, if L is true, then the whole of the OR is true, so we can just return T here. And if L is false, then we have to check whether R is true or not. So it's kind of complementary to and. And again, all the tests pass. And finally, for not. Again, not is very, very straightforward test-wise. And it only takes 1 parameter. We'll call it B, if I can type. And now what we do is, if B is true, we return false. And if B is false, we return true. So that's all of Boolean logic. Now, with all of Boolean logic, you can simulate all of computers. So we kind of know already that we can get there on the desert island. We can survive. But we would kind of like some other mod cons, So we'll try and see what else we can do. So where do people want to go next? Natural numbers options. Who wants options? 3 people. Who wants natural numbers? Many people. Okay. All right. I'll just trust you to remember the bits that we've done, so I don't have to X out all of these. Natural numbers. Okay. So so natural numbers, first of all, are just the non-negative whole numbers. So what I mean by that is 0, 1, 2, and so on. Now, how do we kind of encode them using just functions? So the idea I'm going to give to you is, what about if we encode them as repeated application? So the number n is encoded as a combination that takes 2 things and applies the first thing to the second thing n times. By that I mean, so 0 takes 2 things, ignore the name just now, some more subtle psychological biases going on here, and it applies s to z no times, right? 1 applies once, 2 applies twice. Okay? So this is the pattern that we're going to follow. And then if we look at how we've encoded things, we see that we do it in terms of these 2 combinates called z and s. And z, we can see from this bit here, is 0, because if the mainland number we get is 0, then the the thing we give back is z, so it better be the encoding for 0. And okay, this bit I've kind of given you for free because I've told you here what the encoding for 0 is. So we'll just write that down straight away. S is a bit more complicated. So S is the successor combinator. So you can see from how I'm using it, if n is not 0, again I would assume that we've been, the caller is being nice to us and is just giving us a non-negative whole number, which is, a pretty big assumption, but seeing as we are the only person on this desert island, I think we can hold ourselves up to this high standard. So what S does is you kind of calculate the encoding for the number 1 less than the one we've given, and then we apply S to kind of bump it back up again. So if you give S the encoding of a particular natural number, then it will give you the encoding of the number 1 bigger than it. Well, that's why it's called a successor. So how do we do this? Well, we know that it takes a number and it produces a number. So it starts like this. So it takes a number, so it's a combination of one parameter, which is the encoding of the number. And we know that it has to return a number, so it has to return this thing that has 2 parameters. The question is, what do we do when we have these 2 parameters? Well, we have to apply S to Z however many times n did, and then once more. Well, this will apply S to Z however many times n did. How do we call it one more time? Yeah, we apply S one more time. That's literally it. And that is the entire encoding. I've only got 2 tests, and I have not defined the translation to the other way. That's why that didn't work. So let's do that. We'll have a look at. So we'll follow the same kind of principle we did before, which is that we're consuming the combinator to produce the mainline number. So we know that we have to give it an S and Z. And what we're going to do is we're going to figure out what the S and Z are by kind of working through like the computer does for a couple of numbers. So we're going to do, so n0 I'm going to say is the encoding for 0. What happens if we apply S and Z to that? And we'll do it for 1, and we'll do it for 2 as well. And we know what it should be, right? N0 should be 0. N1 should be 1, and N2 should eventually evaluate to 2 when we apply it to the specific S and Z. We don't know what they are yet. We're going to figure out and do it using this method. So then the question is, what does N0SZ actually evaluate to when we call it? So if you remember, it's the encoding for 0, so it looks like this. So if we apply it to S and Z, then it gives us what? Z, right? So we know that N0SZ gives us Rx, Z. So from this, we know that Z has to be 0, because otherwise things will go wrong if we return anything else. So Z has to be 0. Actually, I'm going to leave it like that now. What will N1 do? Well, it applies S to Z once, right? So it does this. So we want S of Z to be 1, and we want S of Z to be 2. Right? That's what applying N0, 1, and 2 to S and Z does. So from this we know this has to be 0. So we can fill that in everywhere. But we also know from this line what S of 0 has to be. It has to be 1, right? That's what this is saying. So that means we can fill S of 0 in here. Okay? So we have this specification. Z has to be 0. We know that. And S has to be a function that when you give it 0, it gives you 1. And when you give it 1, it gives you 2. Right? And so on and so on. So does anyone have a good idea of what this function is? Ink? Yeah, it just adds 1 to the thing you give it. So that's it. That's how we translate back. Now hopefully... And just to show you that this encoding actually is the one that I initially suggested, that we are applying the functions however many times I said we would, I'll define using Stringify functions and kind of pass them in. Actually. So we know that S has to be a function of one parameter, but we know that Z is kind of, it just goes at the end, it's the thing that gets applied to, so we're not going to use Stringify on that, we're just going to give it a string. And then if we kind of, from a number, actually let's do it for a few numbers. So the first thing we're going to do is we're going to translate it. And then we're going to print out what happens when we apply to S and Z. So you can see here at the bottom, so 1 gets translated to something that applies S once, 2 applies twice, and so on and so on. And just for fun. So it works. Or at least it works like I said it would. Whether it works as an encoding, we'll find out later when we try and define other things on it. So on that note, we have a whole bunch of things we can define on numbers. So we can define any of these things. Parity, is zero, addition, subtraction, multiplication. So I'll go through them each and you can kind of vote again. You have agency in this adventure. So parity. So parity, what I mean is even or is odd. How to define that for numbers. Anyone for parity? 2 people. Oh, okay. What is zero? That's perhaps the simplest one. No one. One person. Addition? 3 people. Subtraction. That's perhaps the hardest thing in the entire talk. Okay. And multiplication. Okay, so subtraction. Okay. The 4 stars there beside me is the most difficult thing. So the reason why subtraction is difficult is kind of the same reason why addition was so easy, but you will never know because you didn't want to do addition. you have dug your own grave. That's all I'm going to say. So the way we're going to define subtraction is using this thing called pred. But the first thing we have to think about is actually subtraction isn't defined for all natural numbers. So if you take the natural number 3 and try and subtract the natural number 5, we get -2, which isn't a natural number. So we're going to kind of, if that happens, we're going to put our hands up and say, you know what, you gave us 2 numbers that don't work, we're going to give you 0. Right? So actually we're not defining subtraction, we're defining saturated subtraction. If it goes below 0, we're just going to return 0. And the way we're going to do it is we're going to do it in terms of this function called pred. And pred is actually a really complicated thing. Sub is, as it happens, is actually super easy. Well, relatively speaking, compared to, you'll see when you see pred. So you have these 2 natural numbers, m and n, and you want to subtract m, let's call them different things. This is a bugbear of mine. Mathematicians always call natural numbers m and n, and then they can't ever talk about them because they all sound so similar. So we're going to call them a and b. Right? We're going to call them a and b, and we want to subtract a from b. Well, that's the same thing as subtracting 1 from a b times. Does that make sense? I'll write it down. Subtract 1 from a b times. Okay? I said it like that because then it fits the pattern of what natural numbers are, because they apply a particular function to a particular thing a particular number of times, right? So the function we want to do is subtract 1. So I'm going to tell you now that pred is the thing that does that. The number of times is b, so we know that b is the thing that we're going to kind of consume in this. And we're going to give it the function pred, and we're going to do it to a. That is actually the definition of subtraction, but actually all the dragons are in pred. So pred, it takes a natural number and it gives you a new one which applies a function 1 fewer time than the one that you gave it did. Now, I don't know if you've ever tried to apply a function 1 fewer time than you already have, but I at least don't have that foresight. So the way we're going to do this is we're going to, so we know that it has to return a number, which means it has this shape. But inside this number, what we're going to do is every time we consume n, because that's the only thing we can really consume in this case, but we're going to consume n to produce a function that, I'm going to use some weird word, abstracts over the last application of s. So what that means is n applies s a certain number of times. What we're going to do is we're going to give you a thing that applies s 1 fewer times and then allows you to pick what you apply last. Right? So you can choose to apply s if you like, but you can choose to apply whatever you want. Right? And we're going to use magical functions f and x to do that. But given that that's what we're going to do, what should we apply last to apply S1 fewer times? Does anyone have any idea? The identity, yeah. So that kind of watches us of our S. It disappears because we gave it the choice, what should we apply next? And it goes identity. So it just gives me the identity of the thing that I had before. Now then the question is, how do we get this magical abstraction function? Well, we kind of we'll work by cases again. So we'll say, what if n is 0? What if n is 1? And what if n is 2? And hopefully from there we can kind of see the pattern. So if n is 0, we know that it gives us z, s of z, and s of z, right? But what should it actually? Those are terrible name choices because I've called them f and x. So okay. So f of x. So we apply f and x n0 to f and x, and we get x. What should it actually be? Well, we give it the choice. You know, we say you can give me a function, and where I would have applied s, I will apply this thing called g instead. That's what I mean by abstracting over the last application. But actually, 0 has no applications of s, right? It kind of just gives you back z. So actually, what I'm going to do is I'm going to ignore the function that it gave me, and I'm just going to give you back z. Yes, and I do mean z instead of x here. Because this is f and x from n0, but we actually already have an s and z here. Okay, what about 1? Well, 1 will kind of, straight away it'll apply g. You can see why this is the hardest section. Okay, and then finally, so n2 kind of showcases like all of the parts. So we have the g, and we have one g, one s, and one z, right? So if we applied this thing that we get to s, then we would get n again. If we apply it to the identity, we'll get n minus 1, right? That's the kind of thing we want to do, because at every stage, right, you can see in here, n2 gets the result of n1 inside it, right? That's what it gets to work with here, right? So we need a way of recovering the number again, and that's why we need this encoding that kind of deals with the fact that sometimes we want the number we had before, sometimes we want one less than the number. So we know what x should be from the first line, like before. So like with the encoding. So we can just put that straight in. I'm actually going to use the const combinator just to prove it has some use, because it seems pretty weird. We don't want it to feel left out. But for this one, so we get this thing h, and h is this kind of abstracted function for the number 1 less. And we want to produce the abstracted function for this number, right? So we know that it is this like comment that returns takes 1g, and we know that it kind of, all of them kind of wrap a g around everything. So we know this much. What goes inside the g is kind of where it gets a little bit confusing. So what goes inside the g? We need to have like a number of applications of s to z. And do we have anything that has a number of applications of s to z inside it? we do. H has it, because so in the case of n1, h is just x. In the case of n2, h is f of x. So in the case of n2, actually what we're saying is if we do f of, and we've actually fed it this thing that applies g to z like this. Right, that's what f of x is, right? So this is the same line as above, basically. But all I've done is I've replaced f of x with the thing that it is from the line above, right? So that's what we have to work with. Well, we know that if we take this thing, which I've deleted, if we take this thing and we apply it to S, we get S of Z, which is the thing we wanted to apply G to. So that's what we're going to do. We're going to apply H to S. And that is the definition of pred. Which I appreciate you probably don't trust me on. So I've got tests. I've got tests to show you that it does in fact work. And seeing as now you've gone through literally the hardest part, and you know what that entails, maybe you will choose differently when we go back to the content page. How are we doing time, by the way?
I think this is the last one. I think we're just 8 o'clock, so you've got 5 minutes.
5 minutes, okay. We've got to do something in 5 minutes. So, do you want to do anything more to do with natural numbers?
What's your favourite one?
What's my favourite one? Oh. Well, I can do pairs in 5 minutes. So right now it's my favourite one. Okay, so pairs. What I mean by pairs is, I guess the closest thing in JavaScript is just an array with 2 things in it. But in other languages there are like special constructs for it. But it's just 2 things packaged up. So if we wanted to define booleans like you had before, like you suggested, we could use pairs, and that would have been a good encoding for booleans. We just didn't have the tools at hand at the time. So really, if you think about it, data structures are only as good as what you can do with the data inside them. And that's kind of, I've not told you this, but that's kind of the philosophy we've been using to define our data structures. They are very much doing things, right? So booleans kind of encapsulate choice, right? Choosing between 2 things. Numbers encapsulate iteration by a fixed number. And pairs, they actually encapsulate a very, very simple thing. They're just 2 values waiting for a function that will accept them. That's how we're going to encode them. So what I mean by that is, if we have a pair with 2 things in it, then that becomes, well, we'll wait for a function, I'm going to call it p, and that we'll wait and then we'll apply the 2 things to p, right? So, well, I've basically given you the definition of this pair complementer then, because it takes 2 things, which were 1 and 2 before, and then it returns this thing that applies p to them, right? And then, so one of the things that it would be useful to do with a pair is to get the things back out again. And that's what first and second do, for first and second. They take a pair and they give you the first or respectively second thing from the pair. So we know that they take a pair. I'm going to call this pair, they both take pairs. And again, this is like a situation where we're consuming the pair to produce either its first or second component. So consuming means applying it to a particular function, and we have to just decide what that function is. So in the case of the first one, so in both cases we're getting the first and the second part. And in the first case, what do? Return the first part. And in the second case, we return the second part, right? Do these things look familiar to you? True and false. They're true and false. That's just a coincidence. I just wanted. But yeah, they're true and false. In fact, actually, if we look at Z from before, a long way before, we have come so far. What does Z look like? Z also looks like false. And actually, if we had done optionals, the nothing case for optionals also looks like false. And nil for lists also looks like false. It kind of looks a little bit like we're nil punning here, but it's not quite that, because if we fed anything that wasn't false to if, so a non-empty list to if, then it would explode. But it's almost nil punning. So that was nice to see. Okay, pairs. So now to do the encoding, what do we do? Again, it's a situation where we kind of have to consume. Oh no. Okay. So this is just actually super simple. It's just a bit of accounting, really. We're just changing the brackets around first and third. That's all we're doing. And in that case, we have pairs. Yeah. That it? Okay. The end. Okay. So. There's actually a whole bunch more. So all of the stuff that I've covered and all of the other sections are in this JS from scratch GitHub with comments for all the explanations I would have made. And then there's my Twitter, which I don't really understand how to use Twitter, but you can follow me on there anyway. Yeah, and yeah, that's it. Thanks.
Cool. Cheers. Yeah, you certainly helped with my imposter syndrome.